This section provides the ideas behind predicting from the likelihood ratios. A separate video shows SQL code for predicting from the likelihood ratios. In this section, we assume that you have thousands of predictors, and for each predictor, you have calculated a likelihood ratio. This brief presentation was organized by Dr. Alemi. Likelihood ratios are estimated from training set, and predictions are made in validation set. These two sets of data are randomly chosen. This process is called cross-validation. Typically, five-fold cross-validation is done. The analysis is done 5 times, each time randomly setting aside 1/5 of the data for validation. The reported accuracy is the average across these 5 sets. Cross-validation protects against modeling noise in the training set. As the number of predictors increases, the chances of modeling noise in the training set increases. Since we have thousands of predictors, chance of modeling noise is large. It's important to cross-validate the predictions. In SQL, random numbers have seed values. If the seed value does not change, the same random digit will be generated. One way to randomly select patients to be included in the training and validation set is to use their ID. One must first convert the ID to a number. If patients are unique, then raw numbers can be used as seed for the random number generator. We rely on diagnosis to predict the outcomes. In electronic health records, one has access to diagnosis before and after observing the outcome. Some diagnoses occur before and some after the outcome. This is not of concern if our outcome is mortality. No diagnosis obviously occur after the patient has died. There are some exceptions like autopsy reports, but in general. A critical question in use of predictive modeling is whether the predictors, the patient's diagnosis for example, should be limited to before the observation of the outcome. Many statisticians advise that in multivariate analysis, independent variables should occur before the outcome of interest. This is not the case when it comes to multimorbidity indices. Keep in mind that a likelihood ratio measures the impact of a diagnosis on outcome. These ratios do not distinguish whether the diagnosis occurred before or after the outcome. In this sense, likelihood ratios are measures of associations. They show the association between the diagnosis and outcome. A strong likelihood ratio does not imply that the disease causes the outcome. It simply says that it is a measure of association between the diagnosis and the outcome. In using the likelihood ratios, there are two ways to use likelihood ratios. In one approach, one tries to detect an event that has already occurred, but perhaps not reported. For example, one might want to detect if the patient has undiagnosed diabetes condition or has an unreported substance abuse disorder. In another approach, one tries to predict an event that has not yet occurred. For example, one might want to predict if certain patients will in the future abuse pain medications. These two approaches differ in what variables they use for predictors. The detection approach can rely on association between consequences of the outcome. For example, it can rely on repeated skin aberrations or an unreported or on repeated infections to detect injections of drugs. Here, the diagnoses are occurring after substance abuse. A particular pattern in these diagnoses points to the existence of substance abuse earlier. The prediction approach is different. In forecasting, one must only use the information that's available. Hence, one should rely on events that preceded the outcome. Consequences are no longer a reasonable predictor. For example, repeated prescription of opioids for surgical pain increases the risk of opioid or prescription abuse in the future. For another example, borderline A1C levels increases the risk of diabetes. In deciding which variables to include as predictors in a multimorbidity model, the first task is to decide if one is predicting or detecting. Of course, if the outcome of interest is mortality, the choice is simple. We are predicting mortality. No point in trying to detect it. In other conditions, for example, predicting diabetes, One set of predictors are useful for detection and another set are useful in prediction. In practice, we rely on thousands of clues to predict the outcome. An easy procedure is needed to understand the combined effect of all the various clues in the patient's medical history. The odds form of the Bayes formula guides how the likelihood ratio of various diagnoses are used to predict mortality. This approach is also sometimes referred to as naive Bayes. We calculate the change in posterior odds of the outcome. This is calculated as the product of the likelihood ratios for diseases within the patient's medical history. Now let us consider more philosophical problems. This problem refers to the fact that estimated likelihood ratios contains a great deal of confounding. If a relatively benign condition tends to occur with a relatively deadly condition, then its likelihood ratio will be distorted. For example, hypertension occurs often in patients who later have heart attack. As a consequence of this concurrence, the likelihood ratio of hypertension will be overstated. We will have a higher probability for hypertension leading to mortality than we should. Procedures to remove confounding are available in several published papers. We recommend the use of stratified covariate balancing in removing confounding, as this approach is not parametric and can be done using SQL. Applying methods of removing confounding remains an active area of research. The other approach is to live with the overstated likelihood ratios. It's likely to be predictive even though people are not dying from hypertension but from heart attack. But since the hypertension and heart attack are correlated, then the error may not be that bad. Since likelihood ratios are average association metrics and not causal, bizarre situations may occur when a disease could have a likelihood ratio less than 1, suggesting, but I want to emphasize in error, that it reduces the risk of mortality. In reality, few diseases help patients. For the most part, there is no such thing as a protective disease. The likelihood ratio is reducing the risk compared to prior odds, which reflects what happens on average. It does not really reduce the risk of death if compared to a non-diseased patient. It's not really helpful to be sick. What it says is that the odds of the patient being sick is less than the average. The odds of outcome is calculated as the product of the likelihood ratio associated with the disease in patient's record. If predicting the event in future, then all diseases before the outcome can be used. If detecting the problem, then the diseases post-outcome can also be used.